Welcome back to The Explainer, everyone. Let's jump right in. Today we're doing a structured, pretty technical deep dive into the architecture of modern fraud detection. You know, if you've ever wondered how the financial sector is actually fighting back against these incredibly sophisticated cybercriminals using engineered data, well, you're absolutely in the right place. We're going to look under the hood of some really fascinating new research to see exactly how these systems are built from the ground up.
But to really get the solution, we have to understand the massive scale of the problem we're dealing with. Consider this number, 90%. In traditional anti-money laundering systems, a staggering 90% of the alerts generated are false positives. I mean, just imagine the sheer operational drag of that. It literally means compliance teams are spending almost all of their valuable time chasing ghosts instead of, hunting actual threats.
And the financial stakes? They couldn't be higher. Just looking at 2019 alone, UK financial fraud losses hit a record high of £824.8 million. To put that into perspective, this isn't just some minor glitch in the matrix. This is a massive operational failure. It's a shared industry enemy. The legacy systems we've been relying on simply haven't kept pace with modern fraud schemes.
So how do we fix it? Here's our agenda for today. We've got a 5-part blueprint. First, the false positive problem. Second, rules versus AI detection. Third, the feature engineering framework. Fourth, real-time aggregation workflows. And finally, explainable AI and shop.
All right, let's start with Section 1, the false positive problem. Let's explore exactly why these outdated systems are failing financial institutions so badly. The core issue really stems from inflexible, static rule sets. Imagine a perfectly legal seasonal business, right? They make a large, routine payment exactly once a year. An overly sensitive legacy system completely lacks the contextual awareness to understand that this is totally normal for this specific client. It just sees a mathematical spike and immediately throws a red flag. Because of these rigid rules, legitimate anomalies get flagged constantly, and the real-world result? A full 32% of a security operations center analyst's day is completely wasted just staring at meaningless false alarms instead of doing actual investigative work.
Okay, moving on to Section 2, rules versus AI detection.
You can kind of think of rule-based systems as the well-intentioned but frankly consistently failing sidekick. They operate on rigid thresholds, they generate those agonizingly high false positives we just talked about, and they suffer from batch-based delays. Contrast that with AI-driven methods. Now this is our adaptable, context-aware hero. AI brings advanced pattern recognition to the table. It has the contextual intelligence to actually understand the history of an account, and it uses real-time adaptation to shift autonomously as fraud schemes evolve.
That brings us to Section 3, the feature engineering framework.
So how do we actually equip this AI hero with the right data clues to succeed? Well, recent research out of London Metropolitan University proves a really critical point. Raw transaction data just isn't enough for an AI model to catch complex fraud. You have to purposefully engineer the data. This framework involves 3 vital steps. Number 1, feature aggregation, which summarizes behavior over time. Number 2, feature transformation, mathematically converting raw data into a machine-readable format. And number 3, feature selection, where we pick only the most predictive data points so the model doesn't just get completely overwhelmed with noise.
To really get feature aggregation, think of it like giving a detective the suspect's entire case history, rather than just handing them a single blurry snapshot of a transaction. By combining things like timestamps, transaction amounts, geographic locations, and access methods, we build this comprehensive profile of an individual user. This contextual baseline is a real game changer, because it makes it instantly obvious when a fraudster deviates from that normal behavior. And the results of engineering the data this way? Honestly, they're staggering. The London Met study found that applying this specific feature engineering framework significantly boosted the performance of machine learning models. We're talking about a massive 40% improvement on the F1 measure, alongside a solid 20% increase on the area under the curve value for models like support vector machines. Actually, scratch that. What this fundamentally proves is that better data, not just more data, is the absolute key to detection.
All right, Section 4, real-time aggregation workflows.
So, the underlying theory is solid, but how do we actually apply this in the real world of live banking? We know we need contextual features, like, say, a customer's average transaction amount over the last hour. But the massive technical challenge here is, how do we aggregate these complex features in milliseconds, literally exactly as the transaction is happening?
To achieve this, modern banks rely on an event-driven streaming pipeline. And it's fascinating how fluidly these components interact. Think of Apache Kafka as your ingestion fire hose. It's handling millions of events simultaneously without dropping a single packet. But we obviously can't send all that raw data straight to complex ML models. It's way too computationally expensive. That's where KSQLDB and Cloud Firestep step in. They act as this rapid response filter, knocking out the noise and performing lightning-fast lookups of historical features. Once that noise is filtered out, the highly relevant data streams directly into Apache Flink. Now, Flink is the heavyweight champion of complex event processing here because it maintains state. It remembers that a user logged in from a new device 5 minutes ago and, say, failed a password attempt twice before executing this transfer. Flink runs the actual machine learning inference right then and there, armed with all that deep contextual state.
This architecture completely transforms fraud detection. It takes it from a retrospective, delayed batch task into a proactive, lightning-fast pipeline. Recent research on this exact setup demonstrated an incredibly precise 94.2% true positive rate. And all of this is happening with sub-second latency. Basically, it catches the fraud before the money ever leaves the account.
And finally, Section 5, Explainable AI and SHAP. Now, even with near-perfect accuracy and blazing speed, financial institutions still face one final hurdle. Banks cannot deploy models they can't explain to regulators. That's a hard stop, and this is exactly where SHAP comes in. Shapley additive explanations is this brilliant method borrowed from game theory. It essentially opens up the black box of complex machine learning models by quantifying the exact mathematical contribution of every single feature that led to a specific prediction.
In practice, SHAP is an absolute game changer. It tells a human analyst exactly why a transaction was blocked. Was it the unexpected overseas location? Was it a suspicious time gap between transactions? SHAP identifies these top predictors and translates all that complex math into clear, highly visual Power BI dashboards. It completely eliminates that black box trust barrier we talked about, ensuring that your highly accurate AI remains fully transparent and fully compliant. We've covered a whole lot of ground today, from the nuances of feature engineering frameworks to sub-second streaming pipelines and explainable AI. I really want to leave you with this provocative question to evaluate your own infrastructure. Is your financial institution simply reacting to past fraud, or are you intelligently predicting threats in real time? Thank you so much for joining me on this explainer. Keep learning, and I'll catch you in the next one.